which is very, very easy with multi-threaded code. And it makes it very easy to maintain and refactor. So if at a second point in time you need to change your code, or you need to change the code that somebody else wrote, the C# job system makes it very, very easy. We showed it a while ago, if you remember this demo at Unite Europe 2016, where we were showing this shark going around and the school of fishes like following some other fish, and that was the first time we've shown it to the public. Then in 2017, we also shown a very, very similar demo, to be fair, which showed this flock of spaceships flying in this sci-fi environment. And that's where we shown, for the first time, another part of the stack, which is the burst compiler. So the burst compiler is a compiler. So basically, 90% of the time, you don't really need to do anything with it, like we do the work for you. And it just compiles your C# jobs in a very, very optimized way, which depends on the architecture that you're building for. So if you're building for a certain type of architecture, the burst compiler compiles in a very optimized way just for that specific CPU. And again, it's not really much that you need to do for it. You just apply a tag to your job and in your code, and then you use burst compiler. And we've seen some speed ups between like 5 and 20 times just by using this different compiler. But the part that I want to talk to you about today, which is one of the most important ones in the stack and one of the most complicated ones as well, is the entity component system. And that's the one that's like really shaping the future of Unity. And that's why I want you to basically get started with it, to start understanding what it means. So we had the problem historically, right? Unity is fine. It has this architecture with game objects, with components. The problem that Unity had, and again, to be fair, it's a common problem, is that when you have this type of architecture, your objects are spread out in memory, in the RAM. And when the CPU needs to work with them, it needs to run back and forth from the CPU to the RAM and bring data in all the time. And this data, because it's spread out, the CPU needs to fetch this data multiple times because it finds just very, very small bits of useful data, and then it has to run somewhere else in memory and bring it in. So the problem with regular Unity is that Unity works fine for now, but we've reached a certain limit. And past that limit, it's really, really hard to scale. But at Unity, we figured out that we want to enable a different level of scale in the games that you're making, or, any application that you're making with Unity. So we needed to find a different solution. So we looked at ECS, which is not a new technology. It's just new to Unity. And the way ECS organizes things is slightly different. It's similar, but different. In ECS, you don't have game objects anymore. You have entities. But they act more or less in the same way. So any objects in your scene, your character, or a chair in a room, that's an entity. And then on the side, you have the components. Again, very much like today. There's a small difference, well, a small big difference, though. The components in ECS are only data. They're not logic. So in regular Unity, what we call classic Unity, the components that you use today, they're MonoBehaviours, right? And they contain the logic as well. In ECS, they're only data. And they sit somewhere else in memory, tightly packed into arrays. So if you have many entities that share the same set of components, they will be in memory together. There is also an array of entities, but the entities are really just an ID. So it's really just one number. And there is an entity manager that looks over all the entities, but I'll tell you why it's not the best to use the entity manager, but you go directly to the components. And so the entities are packed, as I said, tightly in memory based on archetypes. The combination of components puts the entity into a specific archetype, which means that, for example, archetype A is all the entities that have position, rotation, and colliders, for instance, 3 components. Archetype B, only the entities that have position and rotation. And we do all of this. You don't need to do that. Like, that's what the ECS does for you. It just packs the entities in different parts in memory, ready to use, depending on the archetype that they belong to. So as you add and remove components, they get moved. I think I have a, yeah. So if you add a component, for example, to an entity in archetype B, then that entity is moved to the other archetype at the end of the frame. So this means that they always sit together. If they have the same functionality, they will be in the same place in memory. And then when the CPU needs them, it will just find them straight away. And that's where the speed up comes from. Well, one of the speed ups. So where is the logic if the logic is not on the components? Well, it's in another part of the ECS. You know, the S is the systems. So you have entity, component, systems. The systems are, as I said, the logic in the ECS. So they're somewhere else in memory. And what they do is that they run one after the other, and they look for the entities that they need to work on, they grab them, and they operate on them at like lightning fast speed. How do they do that? Well, the ECS, they find the entities they need through what we call entity queries. So they run a query. Are you familiar with databases? It's exactly the same concept. Why is the database fast? Because it knows, it has organized the data like beforehand, and then you run a query, and you just say like, give me everything that has like this, this, and this, or these values, right? Well, in ECS, it works very similarly. When you create your systems, like in this case, I hypothesized a transform system. So this transform system is asking for position and rotation, and it doesn't care who has them. It just wants all of the entities that have those components. So it runs a query, and then ECS finds those entities. So in this case, it's finding these entities here, and it's not finding the last entity, which only has position. So it doesn't fit the query. And it finds them very, very fast because it looks at the archetypes. It goes like, okay, who has these components? It doesn't need to look at each individual entity. So it's not like a find, right? GameObject.find or get component. It just like finds them straight away. These entities are packed together in an array and served to the system. And now the system can work on them super, super fast. And it can also work on them in parallel, right? And using all of the threads of your CPU. So now that it has all the entities, it can just iterate through them quite fast. And the system only sees what it cares about. So you see here all the other components, I kind of like hid them. And also the entity array, the system has access to that, but generally you don't use it. You just look at the components. You only need the entity array when you need to jump from one entity to the other. So if an entity is referencing another entity, then you go back to the array and you go like, can you give me that one, please? And that's actually one of the most expensive operations, and is the reason why we did all of this shift, is the random memory access, right? Because now you need an entity which is somewhere else in memory and you don't really know where. And again, that's an expensive operation, but sometimes it's needed. But generally, in ECS, the way you need to reason about gameplay is this way. It's like, system only does one thing, and only cares about component A, B, and C, and that's it. So, this was a very, very fast run-through through the ECS. So the future of game objects and MonoBehaviour script. In the future, that's what we're going to have. We're going to have ECS, and game objects and MonoBehaviours are going to disappear. But don't worry, this is going to take a while. We are transitioning to this model, but it's going to take some time. So what's the cool thing about ECS? It keeps the component-based approach, meaning that any entity can become another type, right? You can attach and detach components just like you do in Unity today. So it's the same workflow that you're used to. The data layout, the optimized data layout makes it super fast. The separation of data and logic, the fact that components don't have logic anymore, means that you have more reusable code. Because now your system doesn't need to care about which entity it operates on, but it's just functionality. And if you need that functionality somewhere else in your game, or maybe in another game, or maybe in another prototype, maybe you're building prototypes one after the other, and you're like throwing away things and you're reusing things. And the fact that the data and logic are separated means that you can reuse more easily. And obviously the ECS leans on the job system that I mentioned before to make all that it does multi-threaded. So that's why it's also very fast. We shown ECS for the first time at Unite Austin 2017. Do you remember this demo? The big battle made in collaboration with the Serbian studio Nordeus. But at that time, everything was made in code. So everything was made by like our CTO, Joachim, and a team of people, like super fast. They created these systems, they created the movement, the nav mesh, and even the animation was made in code. Like the animation was made by an animator, and then it was baked to a texture, and then it was read by a shader. So everything was like really programmer oriented, and no artist was working on this thing basically. And that was a problem. We figured out like we can't just make a system that only programmers can use. We need to cater to all of our users, to designers, to artists, to level designers. So ECS is now evolving, and we're looking at editor workflows. This has been the big focus of 2019 for us. Do you know this demo here? Have you seen this one? Who has seen Megacity? A few people. So Megacity is a demo that we shown at, I think, GDC 2019. It's a huge city made of 4.5 million renderers. So 4.5 million is a number that in Unity, without ECS, you will never see. Like you can write it in a text box, but 4.5 million objects, you can't have them. The editor would explode. And it's because, you know, like every object has a cost. And with ECS, we're looking at lowering that cost. So Megacity leans on ECS heavily, but one thing we wanted to achieve with Megacity was we wanted to give artists the power. We wanted to give them a way to create these buildings, not in code, not program them or, you know, through a JSON or whatever. They needed to be in the editor and actually place game objects and maybe use prefabs and maybe use nested prefabs. You know, all the power that the editor offers you, we need to make it available to the artists. So you see here like huge buildings. Each one of them is made of like 20,000 objects. And again, total is like 4.5 million thousands. So how do you make that available to artists? Sorry, we shown at Unite LA this year. This year? Last year? I don't remember. So, so basically what we tried to do was to go through editor workflows. And the idea is, on one side we have what we call Unity Classic, like game objects, MonoBehaviours, and all of the tools that we have today for Unity. As I said, prefabs, and all that stuff. On the other hand, we have DOTS Pure, which is like using none of the game objects functionality. So how do we bridge these two worlds? And we figured out we're going to use, for the time being, what we call the conversion workflow. So the point is, you use game objects when you edit in the editor, and then when you press play or when you build, you know, when you're playing the game, you use entities. So game objects are converted into entities, both the game objects and their components, right? And this has a lot of advantages. I mean, I don't want to go too much into detail on this, but there is a point in having data in a certain way as you edit game objects and in a different way as you run the game. I'll give you one very quick example. Rotations, right? You want rotations to be X, Y, Z. And what is that? It's a vector 3. But the machine, what it wants is a quaternion, which is 4 values, which are not humanly readable, but they work for the machine. They are the best for the machine. But you don't want to edit quaternions. So there are 2 sets of data that you need to deal with. And that's what we thought was a good direction to move towards. The nice data to see in the editor and the optimized way to run things in the runtime. So that's what the conversion workflow allows you to do. Conversion workflow is a one-way conversion from game objects to entities. And so after the conversion happens, the systems in ECS do what the MonoBehaviours should have done, right? So they take control. In conversion workflow, we convert some Unity systems for you. So if you're just using transforms or mesh renderer, we do that for you. And we're going to provide more and more built-in converters if you want. But you have to write the conversion scripts for what's missing. So if you have a script that does something specific, you need to provide the equivalent system. And that's on you to write, because you need to port your code to ECS. And also you provide a way to convert the data. So you say, for example, this vector 3 becomes this quaternion. This float becomes this float. You know, and you decide. You decide how to convert. You decide how to fraction the data, because maybe one big component in game object becomes multiple smaller components in ECS. And that has a lot of sense. That's not something that we really can do for you. Like, you know your game, you know your gameplay. So we are providing more and more systems, rendering, transform, animation is going to come. Well, animation is already here in some way. Physics is already here, and then we're going to provide more and more and more. And then you will provide what's unique to your game. A tool that we offer is subscenes. Subscenes are basically, they look like a scene, if you want, that can be opened and closed. In Megacity, we use them for the buildings. And they look like that on the left. They look like a regular game object. On the right, the inspector shows a button, edit, right, which is here. And if you click it, what you get is this. So basically the subscene, when it's closed, it's entities. It's, again, tightly packed in memory, super efficient, only the stuff that the machine cares about and nothing else. And then you can have many. When you open it, you're asking to recuperate, in some way, the original game objects. So subscenes are containers of game objects that on demand you can close and convert to entities. And on demand you can reopen them and grab the game objects again for editing. Yeah, so a subscene is just a game object with a script which stores a number of game objects in memory as entities. And on demand, it can revert back to game objects if you need to edit them. And it gets back like all the prefabs, all the connections. So if you're using prefabs, you can just use them as you're used to, which is what we want for designers and artists and stuff. So you can then scale from a single prefab, which in Megacity looks like this, like it's super detailed, to like maybe 5-10 objects, and you compose like a prefab that's like what we call an undressed tile. Then you scale up to 60 in each tile. Then you're building a section of a building, which now has 1,200 prefabs, which starts to be quite a lot, to 50,000, which is where your editor starts to struggle, depending on your machine, I mean. But normally, a Unity game with 50,000 objects is like, slow down, like maybe you need to optimize somewhere. But with ECS, you can get to that scale. And so the buildings in Megacity are a subscene, and they look like this, and they contain roughly like 50,000 to 100,000 objects. And that's what allows you to have 4.5 million objects in the final scene at any time. So you're in the editor, and you see those 4.5 million objects, and you can interact with them. Not individually, you need to open the subscene, but you can have them there. So you can composite your scene, you can move things around, and you can see how they look in the final layout. Authoring components, they look a bit like this, just to give you a taste of what they look like. So I'm also very short on time. They look like this. As you can see, they're MonoBehaviours, regular MonoBehaviours. So you attach them to objects, and they take from this interface, I convert game object to entity. So then the system is going to come in and convert it for you. And what you need to do is you need to provide the authoring data, so the nice human-readable variables, human-readable data that your designer is going to use, for example. And then you have this function, convert, which converts, and converts it the way you want. And so that's where you do your work of conversion. And that's where you decide what data becomes what in ECS, right? So in this case, for example, you can see I'm using, I think I have another, oh yeah, you have a destination manager that takes care of like what's going to happen on the ECS world, and you can ask like, please create an entity, please attach a component, please put this data into this component here. And that's what you see here I've done with the, I don't know if I have another, yes, the add component data. I'm adding a new component called speed, which is taking the float from the, the int from the speed, the public speed that I have on the MonoBehavior, and it's putting it into this new ECS component called speed, exactly the same. This is a very simple example, but it can become more complex. But again, it's up to you to decide how, right? We can't really decide how you decide to pack your data or or how your game runs. So this is a very simple example of an authoring component. How to create gameplay in ECS? This is a tough question, and it's a question that we're getting more and more as people explore ECS and they like it. They're like, okay, I understand the tech, but I need to make a game. How do I make it in ECS? And for the purpose of this, answering this question, I created a small game the past 2 weeks, a mobile-first game, which looks like that, and it's basically like a small action game where you roam around, you fight with these enemies, and you use subscenes to compose your scene. And the gameplay is completely driven by dots. Not everything is driven by dots, but the gameplay is. While some other things, which I couldn't do with dots, as I said before, we're in kind of a transitional phase. Some other things I've done that with just regular game objects. And then I make them talk to each other. So what are the common needs of creating gameplay? Well, typical problems that you have that you need to do all over and over again, right? You need to, from an object, you need to find another one, you need to find the reference, you need to find, for example, the closest object to that entity. And then you need to get data from it. Then you need to have these two objects speak to each other. So maybe something happens and to an entity, and it wants to notify the other objects. You know, for example, entity A attack entity B, and it sends damage to that to the other entity. So yeah, changing values of a component, adding or remove components, like the classic stuff. So creating gameplay the DOTS way, right? While in MonoBehavior you used to have components that are like independent in some way. So in the update loop, they do all that they need to do. And they do it on themselves. They can do it on other entities, right? Like get component, and you find stuff like that. And they can modify data on other objects. That's not really possible in DOTS. So in DOTS, you think of the gameplay loop as a conveyor belt. Imagine like a conveyor belt, right? And the components, they run on the conveyor belt, and the data that they contain is processed by the systems, one by one. So systems have a specific order, and they run one by one, and they touch the data, and then they pass it to the next system, and they touch the data again, and they pass it to the next system. So in ECS, you have lots of small components, you have lots of systems, each one has its own concern. So each system does one thing, is worried with only one operation. I am the transform system, I only move things around, I don't care what they do. I am the render system, I only render things. I am the, for example, input system, I only record input and I store it. And I don't know what that input does, I just pass it on to the next system. So you have lots and lots of systems. The cool thing is that you control the order very tightly, so you always know if data is broken in some way and it's not the data you expect, you can always go up the order of system, I have them here, and you can always trace it back and see like, okay, who touched this data? Was it this one or this one? And you can go back and forth. So in my game, I have these systems here. As you can see, I think they're like 14, and they drive the gameplay. And systems are also divided into what we call system groups. So you have 3 main groups that you can put your systems into. All right, so now is the tough part. I really have just 5 minutes. I can just give you a very quick taster. So this is what the code looks like, just to give you an idea. And I want to show you the components. Can you read the code? I think it's big enough. Components look like this. So as you can see, you have stuff like movement input. And this is a component, but it only contains a float tree. This is only storing the input from the player and nothing else. Target is a classic component that has a reference to another entity. It just stores the ID of the other entity. You have bigger components for sure, but as you can see, many components are just like one value. And that's quite important because then you're able to separate things more clearly, and systems can only look at really just like the data that they care about. You have components that are empty, as you can see, and they're tag components. These are only used to say, this entity is the player, this entity is the enemy. And the cool thing with tags, differently from game objects, you can tag entities with multiple tags. So an entity can be at the same time the player and the, whatever. And then the systems look like this. So this is, for example, the busy systems. It's the system that takes care of entities that are busy. And so, again, very short on time, so I'm only gonna go very fast. The job is here. And as you can see, this job, in the signature of the job, you can see that it takes care of busy components. So you know that this system only touches busy components and nothing else. And this is quite fundamental. I found it very nice to work with because at this point, when I have a trouble with busy components, I look into this system. When I and I know that the problem is going to be there somehow, right? Because I know that the data that is coming through this system, I know the type. And I know that this system is not touching any other component anywhere, which is something that instead in regular game object code you can do. And that can cause you trouble sometimes. If a programmer comes and just adds like one line, gameObject.find.getComponent.whatever, now they're injecting their logic into your logic, and you might not know. I mean, if you have 10 scripts, it's easy to find. When your game starts becoming big and you are a big team, then this system really helps with clarity. Again, I don't have time for show you all the code now. I'll show it to you tomorrow during the lab if you wanna join me. So the advantages of creating gameplay in ECS is obviously the performance. As I said before, plenty of optimization in that front. The code is very reusable. It's very easy to refactor and to debug because you have a lot of clarity on where things are happening. You have a lot of clarity on the order at which things are happening. And you can literally, I want to show you one thing. If you go into the entity debugger, the scene is empty, so I need a scene that's actually... You see here, these are the systems that are currently run on my game. And here I can see the queries that these systems are performing and the entities that they're finding. So here I see clearly the order of the systems. I see, you see the zoom? I see the performance. I see how much it takes to run that system. And this gives me a very, very clear idea of the performance that that system is taking from my main loop. And then I can turn them on and off. Because they're so compartmentalized, I can actually turn a system on and off, and it doesn't create any, compilation error or generally not runtime errors. So that really allows me to isolate and focus more on where the problem might be. The drawbacks, I have to be honest, I want to be honest with you, are that at the moment, there's a lot of code to write. When you write code in ECS, you generally need to write more code than in MonoBehavior. And most of the code is not your functionality, it's like boilerplate. It's like the header of the class, the signature of the function. So there is a lot of code to write, and we are working on that. We want to provide you with faster and faster ways to write code, potentially generating it for you or shortening the function calls and stuff like that. The other drawback is that it doesn't interact with all of Unity features. And again, that's something we're working on. We're creating them as we can, because of time, and also because we wanna create something that's final. We don't want to give you something that's temporary and then we change it down the line. So just to finish, I think I have 4 minutes. So where is DOTS headed? Lots of cool stuff is coming with DOTS. One of them is Live Link. Have you seen this stuff here? Unite Copenhagen just 3 weeks ago, I think. We unveiled this new technology. So because the data is now separated from the logic, what we can do is we can take the scene, you make a change, we convert it into entities, and now we have a photograph of the data. And we can make a diff with the data that's, for example, on a device, on a phone. So you have the game running on your phone, the game is running, the logic is running, and you're in the editor, you live linked the two things, make a change, maybe you move an object or you attach a new component, we convert to entities, make the diff, and then send the difference to the device. So now you can make changes on a running game on device, on a phone, on a console, and that's super, super powerful. Because now you can literally you're a designer and you want to see how it looks on the device. You just literally save the scene and you have it on the device. Does it look good? Does this shader look good? Does the position of this object make sense? And what's the impact on the performance? You could be profiling the thing on the device live and make a change, save, and see how the performance changes. Super, super powerful. And it's only possible because data and logic are separated. We are converting many features to ECS. This is a demo that we unveiled last Unite. So we are converting physics. We already have rendering and, physics are already there. We're converting animation and terrain are probably the next candidates. So we're moving features as we can, as fast as we can, to ECS world to give you more and more power in what you can do with ECS. And as I said, some things you still need to do them with regular game objects. So this demo was showing, physics and animation and netcode as well. The other thing that I wanna very briefly mention is we have these two worlds and we have the conversion world. And what happens is that These are inverted, actually. In regular classic Unity, you're using a runtime that is big. When you build a game, you're bringing with you a lot of the Unity libraries, and you can't really leave them behind because they're kind of like tangled between themselves. But as we move to a more ECS world and a more packaged-based world, what happens is that because all packages are isolated, you're able to leave them out. So what we're able to do is we're able to have a new runtime, what we call the DOTS runtime, which is basically the runtime with kind of like 0 size, and then you add functionality as you need it. Now, what's the problem? Today, as you use the conversion workflow, because you're still using some systems that are part of game object world, you still need to be on the classic runtime. But as we move on, in the future, we'll be able to unlock this new runtime, which is going to be super small. That's super useful for example, if you're making mobile games and size is really, really important. Sometimes, the size of the Unity runtime, which I think is like 30 megabytes, for a mobile game is super important. It adds to the game so much that then sometimes some studios choose not to use Unity just for that reason. So we want to move to a situation where the DOTS runtime is going to be so small and you only add the functionality that you need. And that's when you're going to be able to use like pure dots and basically work with game objects in the editor, but when you build, you only use entities. Visual scripting is part of the picture. So when visual scripting is going to be ready, it's only going to be for dots. It's built for the ground up for dots, and what it does is that it produces, generates production-ready code as you work on the graph. So one of the side effects of visual scripting is going to be that if you want to learn ECS programming, you can actually use visual scripting to work. You see the code that it generates, and you kind of understand what the difference are. And as I said, production-ready code, it means that because it's optimized, because it's ECS, you can actually put that code into your final game, and it runs as performant as the code you will write yourself. And this is something that we really, really want to focus on, because we don't want to go towards a model where the artist creates the visual scripting graph, and then somebody has to come in and clean it. We don't want to do that. So, conclusion: why care about dots now if so many things are missing? It's a work in progress. Fair enough, if you want, but I think it has a point to look into it at least. So, if you're a small indie studio, or if you're a solo freelancer, for example, you can start using dots in your game today and maybe offload just some specific operations. Something that's very, very expensive, maybe an AI calculation that you run over and over and over every frame, and the AI doesn't really touch any Unity system. It just makes calculation, maybe based on position, maybe based on array casting. You can do that in dots. And then you pass the result of that to your regular game. And now your AI is super fast, right? The other thing is, of course, getting ready for contract work or working with dots in the future. That's something that we predict is going to come in the next year and a half. There's going to pop up, work opportunities that are related to ECS and dots. So that might be something interesting if you're still studying, if you're looking at the start of your career. And yeah, for bigger game studios, of course, dots enables a scale and performance that you couldn't achieve before. I don't know if there's anybody from a bigger studio. So that's all from me. I really ran out of time. Don't forget that tomorrow we have this thing, the Unity Lab. You're still on time to subscribe, I think. I think it's not full. And we're going to take a better look at the code, a better look at the project. I'm going to give you the project, and you can experiment for yourself, and you can take it home. This is a feedback form. If you want to do me the favor of filling it, that would be great, to know if you liked the talk or what can I improve. This is all from me. Thank you.